University of Florence. His research interests include quantum computation, quantum communications, quantum many-body systems, and machine learning. Today, he will talk about generalization in quantum classification, a quantum information perspective. Let's welcome Leonardo.
Thank you. Thanks a lot. Thank you. It's really a great pleasure to be here and to talk with you about these recent results. So the bulk of my talk today will be based on the following paper that you see together. So it has been done together with Jason Pereira and Stefano Pirandola, and it has been recently published in PRX Quantum a few weeks ago. So you can also access an archived version of that paper, which is, I think, pretty up to date, by using your smartphone on the QR code here on the right. So today I'll talk about the generalization in supervised quantum classification, but using tools from quantum information theory. Okay, so let me start very slowly. So slowly that, I mean, this is a slide which is, I mean, not even about quantum physics. So I don't know if you like old Italian spaghetti Western movies, probably not. But if you do, then I'm sure you know this movie here from the 60s, which is The Good, the Bad, and the Ugly. And there is a recurring joke in this movie that basically you can always divide the people in the world between two kinds. So there are always two kinds of people. And now how the people in the world are divided in two kinds may change, and actually changes throughout the movie. But I mean, it's always a variation of people with loaded guns and people without guns. And of course, those without guns, they have all sorts of problems. Now, let's assume that even quantum states can also be divided between two kinds. So there are also two kinds of quantum states, and how quantum states are divided between two kinds may change according to the problem that you're trying to solve. So for instance, one may be interested in certifying whether a state is entangled or separable, or if you are more in the quantum many-body or condensed matter community, you may be interested in deciding whether the ground state of a many-body system comes from a critical versus not critical model. So what can we do? So what's the assumption behind the theory behind this talk? So the assumption is that so you have a machine that, given some inputs, so X here are the external inputs, the tunable parameters. So given some external inputs, so it outputs some state, rho of X. And then the task is to decide whether this state belongs to either the first class, class 1, or the second class, which is class 2. Now, of course, in some cases, there are analytic solutions to this problem. So for instance, if you are interested in certifying whether a state is entangled or separable, you may define what is called an entanglement witness and check whether the state is entangled or not. But entanglement witnesses are state dependent. So you need to have full knowledge of the possible set of states in order to define such a witness. So here, on the other hand, we do another approach. So we assume that there is no theory. But what you know is that somehow an experimentalist, some clever experimentalist, was able to perfectly or characterize very well the states for some particular values of the input. So he was able to say that, for instance, when we use a certain input x1 or x6 or x5 or whatever, then all of these states belong to class 1, while other states, x2 with x7 and so forth, belong to class 2. So now the question of this talk is the following. So given only this knowledge, so you have no theory about how these states are done, but you have this knowledge. So you have a bunch of states which belong to class 1, a bunch of states which belong to class 2. So what can you infer given this partial knowledge about what is the class of an unknown state, which is the rho of X? Okay, so this is somehow the theory question. And the theory question, in more quantitative term, is how difficult is to obtain a reliable quantum classifier given this partial knowledge from the data. Okay, so this is basically then a data-driven supervised classification. And It's related, though different to, let's say, something which is well studied, so the problem of quantum state classification and hypothesis testing. But the difference is that, so here, so we use a training set, and the main task is not to perfectly recover the true class for the states in the training set, but rather to build a classifier that is able to generalize well. So namely, that is able to assign the correct class even to unseen input states not belonging to the training set. Now, the study of generalization is basically the most important aspect in machine learning, at least in my opinion. So it is what makes machine learning different from a mere optimization problem. So the main result of my talk is basically twofold. So we formalize supervised quantum classifiers using tools from quantum information theory, like entropies, data processing, and so forth. And the main technical result is a bound on the generalization error, which is basically the out-of-sample classification error, that depends on the Renyi mutual information between the parameter space X and the Hilbert space Q, where the quantum states live, as it is shown here on this equation. So in other terms, in order to get low generalization error, so we need a number of training samples that is much larger than 2 to the power of the mutual information between X and Q, which then can be interpreted as somehow as a measure of the training complexity of the model. Okay, so let me clarify also another important difference between the problem that I've just described, which is data-driven, and quantum state classification. So in quantum state classification, the states appear with some known probability distribution, either P of X or P of X and C, and see if we have also the class. And then the optimal discrimination strategies can be analytically constructed using for instance, the Hellstrom measurements for binary classification problems, and suboptimal choices, which are still pretty good, can be obtained with indeed pretty good of square root measurements. But here the main difference is that the P is unknown. Okay, so we just have some correctly classified samples, and we need to build our classifier using only this partial knowledge. So in other terms, in quantum state discrimination, we don't have to worry about the generalization. So here we do. Okay, so before introducing the formalism, let me show some example applications. So the first example is the one that I have already mentioned. Like we have a device, and given some experimental parameters, so we have to decide whether the output state rho of X is entangled or not. And then we have a training set of correctly characterized samples, and the question is then, what can we do for new samples? These are already mentioned. So another application which I am pretty much interested in is for quantum channel discrimination, which is a very general topic with many applications in quantum information science. So consider this following example. So we have a self-driving car, which is enhanced with quantum sensors. So the parameters X, so what I call X here, represent the objects living in the physical world. So here, quantum light, possibly entangled light, is used to screen the outside world. And this light will be partially scattered and partially reflected, but some photons will go back to the detector inside the camera, and the state of these photons is what is called the rho of X here. So the state detected by the car will depend on the objects, X, and the task is to make a decision based on those objects, like stop the car, turn left, or turn right. Now, this example might seem like blue sky or something incredibly complex, but there are related proposals, simpler, that have been experimentally tested, such as what is called the quantum illumination, quantum radars, where in this case, quantum light was shown to provide an advantage for target detection. So obstacle, yes or no. Okay, so quantum light can also provide an advantage for barcode decoding and pattern recognition, as we have shown in this recent series of papers. So in these papers, so we consider, for instance, a model of a 1D barcode or a 2D barcode, which is like a QR code. And so we consider the physical description of this problem. So each pixel here in the barcode, which is like this, can be represented as a quantum channel that scatter light in a different way depending on the color, namely, for instance, a different wavelength. So we did show in this series of papers that the physical pattern recognition task, such as using light to perform handwriting recognition, is significantly simpler than decoding a barcode, because somehow you don't have to get full information about each pixel, and errors are tolerated in some sense. So for instance, if a human eye is able to instantly recognize that all of these numbers here are a 4, even if some pixels are randomly flipped. And same again from here, you can see that this is a 9. So we were able to formally justify this intuition by showing that the lowest possible training error depends on the fidelity between the two states that describe either the black or the white pixel, but to the power of the minimum Hamming distance, namely this part here, which is basically the number of bits that you have to flip to turn a 4 into a 9. So because of this power, the error is much, much smaller, even for large fidelity. And so that somehow proves this intuition that errors here are tolerated. Now, from a practical point of view, the optimal classification can be performed by, I don't know, using some entangled states, then some circuit, POVM, and then even some classical post-processing part. And in our papers, we used the convolutional neural networks, which worked, pretty well for this kind of problem. So another example, which is quite popular today, is to use quantum machine to classify data and look for possible algorithmic advantages. So this time, the classical parameters, so what I call X, represent the classical input data, like, for instance, an image. And the task is to decide whether this image is, for instance, a cat or something else. Now, the quantum part consists in first embedding the input data, so the image here, using a parametric quantum circuit whose gates depend on the input, and then perform some measurement at the end. So here we assume that we can model the measurement as a POVM, whose outcome is the class C, which is the predicted class C of the input X. Now, in the literature, this POVM is typically implemented via Naimark dilation theorem, which basically tells you that every POVM can be written as a unitary matrix on a bigger space, followed by some projective measurements on some ancilla. Okay, so the last example is that of many-body physics. So, for instance, in this paper by Kong and others, so they proposed the problem of quantum phase recognition. So basically to detect whether indeed the ground state of a quantum many-body system belongs to different models. And the task here is to decide, what is the phase depending on the parameters of the model. So here the parameters are, for instance, these, which are the magnetic fields. And these external parameters, so these fields represent what is called the X in our formalism. So these are external parameters in the model. So the final example that then we studied in this paper is that we can use machine learning to estimate the entanglement negativity from a few carefully defined measurements, which are the moments of the partially transposed density matrix. So we show that somehow even this partial knowledge is enough for some particular states to obtain a good estimate of entanglement. Okay, so let's now jump to the results part. I've shown that somehow our formalism is quite general, so it can describe many different physical scenarios. So now we formalize the problem a bit more mathematically. So remember that we have a training set. So this training set is made of T correctly classified pairs. So this is the training set. So it's made of pairs. So we have a bunch of states for some particular inputs and the corresponding true class, which we believe is properly classified. And so we have T. So T is the number of pairs in this training set. So we can build a classifier from these pairs and then numerically check generalization by studying the classification error with the testing set, which is basically similar to the training set, but with different pairs, which are unseen by the model during the training. Now, to fix the notation, so here when I say I use a quantum embedding, I'm referring to the mapping between the classical input to the state of X, although in general we simply have parametric quantum states. And while we perform a classification using a P of M whose outcome C is the predicted class, as described before. So the big question, of course, is what can we expect? Now, let's define a loss cost function. So for a fixed P of M, the probability to get class C for a given state rho xk in the training set is given by this expression here. And so the empirical loss, which is actually also the training error, is a sum over all the probabilities to get the wrong outcome. So namely where C is different than the true class ck of the input xk. So averaged over all the elements in the training set. And this, of course, can be simplified via the properties of the P of M. Now, so to study the generalization, we also need to introduce the abstract average loss, which is a kind of the real classification error. So why is this abstract? Because we don't know the data probability distribution. So we don't know this P here. And we only have some independent samples from the training set. So the abstract classification error is the one typically employed in quantum state discrimination, where the optimal P of M is well characterized by Hellstrom and pretty good measurements, for instance. Now, for a fixed, So for a fixed embedding, the optimal measurement to minimize the training error can be analytically computed. Sorry, I'm still going. Yeah, can be analytically computed by what is called empirical risk minimization. So you take the measurement that somehow minimizes the empirical risk, namely the training error. And this again can be done using, for instance, Hellstrom or pretty good measurement. So here I call this measurement PT, pi t, where the dependence on t somehow reminds us that it's constructed from the training set. So I can also do the same for the abstract classification error and construct the optimal measurement, which is what I call the pi star. So this would be the true optimal classifier, but we will never be able to find it simply because we don't know even how to write the abstract classification error because we don't know p. So in this language, then the testing error, which is this one here, is basically the average over the testing set. So it's something which basically has the same functional form of this training error, though the averages are done in the elements in the testing set, and where also we use the optimal P of M, which is constructed during the training. Okay, so this is a very important point. So that's somehow the formal definition of the testing error. And then, we can also, using these definitions, we can also study generalization as a function of the complexity somehow of the embedding. Now, you will see this picture many times in my talk in order to summarize what I'm talking about the different errors. So here we haven't defined what is the complexity of the embedding, but we can expect that with whatever notion of complexity, the classification error, namely the training error, should decrease for more complex models. Like if you have a neural networks with much more parameters, then normally the training error goes down. So the formal classification error then and the training error then basically shows the same trend of this red curve. Now, the theoretical minimum error that can be achieved by any statistical argument is what is called the bias risk, and is what is written in this dotted line at the bottom. So the difference between the red curve and the bias risk is what is called the approximation error A. Okay. Now, if you have an infinite amount of training data, and an arbitrary complex model, then basically the bias risk is the error that you would get. So on the other hand, the average testing error, so which is the light blue curve here, is basically the average loss with the classifier built from data, but so namely from the training set. So by definition, it cannot be smaller than the classification error. And the difference between the light blue and the red curve is what is called the generalization error here. So I will tell you also in a moment why we expect this this behavior here, but somehow the average testing error somehow tells you how the data-driven classifier, which is this pi of t built from the data, is different from the true one. So now we expect this behavior here. Well, I mean, this is the result of classical statistics somehow. So the behavior of the training and testing errors can be understood from what is called the bias-variance trade-off from classical statistics. So consider, for instance, this set of points. So you may use a very, let's say, a very complex polynomial to fit this function, but this, I mean, will result in overfitting. So you can also obtain something which is a trivial constant model, like this one here. And this, I mean, of course, is too trivial and will have underfit the data. So according to the classical theory, there is always a trade-off like the one shown here, which is a good balance. So this is the result that somehow you don't have to use two complex models, but there is always a sweet spot in the complexity of the model that defines what is the best result. Now, I won't study here what happens in what is called the deep learning regime, because in the deep learning regime, I mean, you know that neural networks are something which are incredibly complex with millions or hundreds of millions of parameters, but they also generalize well. And the understanding is that somehow there is a transition at the interpolation threshold, after which somehow more complexity is also good. So I won't study here what happened in this regime, but just to show that, I mean, I don't know here how this curve may behave for quantum model. So we are not going into that regime. Okay, so in this slide now I summarize what are the main results of our theoretical analysis. So we have shown that the generalization error, so the G, is bounded by this B quantity divided by the number of training samples. And I mean, this part here, I mean, it's like a probabilistic guarantee. I won't discuss about the second part here, but I mean, it's just to say that this bound happens with sufficiently large probability. While the approximation error, A, depends on some properties of the average encoding that I will describe in a moment. So both the quantities entering in the generalization and approximation errors can be expressed using entropies. So the B quantity depends on the mutual information between X and Q. So this is the Renyi mutual information, the Renyi true mutual information between the quantum embedding and the classical input space. So while the approximation error depends on the mutual information between the class and the embedding space. Now, all of these entropies are defined, and everything here is defined with respect to this classical quantum state, where somehow C is the class space, X is the input space, and Q is the space where this row of X live. Okay. So I won't show the proof here, so you can check the papers for further details. So I just want to say that somehow our bound has been obtained by combining, I think in a new way, the Rademacher complexity from statistical learning theory, operator inequalities like operator monotones, so tools from quantum information, and in particular the following lemma, which is kind of new to the best of my knowledge. It tells us that basically the average one norm of some operator is upper bounded by this trace expression. And this is basically an operator version of standard generalized means inequality. So if you use this, then you basically get the bounds that I did show for the generalization error. On the other hand, the approximation error, the approximation bound is obtained using more standard results, like the Hellstrom theorem, the mean entropy, and entropic inequalities that, I mean, mostly discussed in this paper by Koenig. While the definition of the Renyi mutual information that we used in the paper were somehow discussed in this paper by Berta and others. Okay, so let's see what kind of theoretical conclusions we can get from our analysis. So the first one is that good embeddings should maximize the mutual information between the class space and the embedding space, so this one here, and minimize the mutual information between X and Q. So basically, good embeddings should compress the input space as much as possible, throwing away all the information about X that is unnecessary to predict the class, which is kind of intuitive, I guess, right? So, but here somehow we have a proof. So this is also similar to how the information bottleneck principle works from classical statistical learning theory, as we will also see in the following. Now, let's consider two extreme cases. So in the first one, all inputs here are mapped onto orthogonal vectors in the Hilbert space. So by definition here, the space X and Q are the same. And so one can prove that basically the approximation error here is minimum, but the generalization error is maximum here. So somehow we are in this regime in this picture. Okay, so very zero approximation error, but very large generalization. So while on the other hand, the trivial constant embedding, where somehow all the X are mapped into the same state with no knowledge of X, this model is, of course, trivial. It has a maximum approximation error, but minimum generalization error. Because, of course, if the model always outputs the same outcome, then it's trivial to learn it from data. But I mean, it will still be a very bad model. So in this extreme case, we are kind of here. Okay. Okay, so then I might be a bit late, so I won't discuss too much this slide. So just to say that so far I've only considered this what is called the single shot linear loss, but we can also put nonlinearities in that quantum language, nonlinearities with respect to the state, I mean, if we use many copies, like n copies of the same input to perform the discrimination. Now, we were able to show that basically if we use n copies, then the approximation error decreases exponentially as a function of n. But we still don't know what happens to b. So we have a conjecture that somehow, depending on the data distribution, so this b might increase polynomially. And if this is true, I mean, this would be a very good result. Or even this can also increase exponentially as a function of the data. So what's the reason because of this conjecture? Well, because there is a related classical result, mostly discussed in this paper, where somehow they show that this entropy, mutual information based on observations, also have indeed these two regimes, which somehow would turn in the quantum language in these two. So this is just a conjecture, okay? I won't discuss it too much, but I'm happy if you want to answer some questions if you have. Okay, so let's now jump to to check. We have also done some numerical experiments to check basically our theory. So we first check one prediction, namely that if we increase the dimension of the Hilbert space, then we get lower approximation error in general, but larger generalization error. So we have performed a very simple numerical experiment where the data of two given classes, which are C equal to 0 and C equal to 1, are Gaussian distributed. So we use a simple embedding called angle encoding. So for a given X, we have this, what is called the angle encoding. And then we also take copies of this simple embedding in order to make the problem a bit less trivial. So we have numerically shown that basically the approximation error exponentially decreases with n. So these numbers here, 1, 2, 3, these are n. And so you see that basically R, which is the risk, which is connected to the approximation error, decreases as a function of n, while the bound on the generalization error, which is given by this b, increases, though increases, I mean, with much more slowly than the decrease of the approximation error. So as another application, I mean, we can formally prove some very intuitive results that, for instance, low dimensional embeddings and low entropy datasets generalize well, which is kind of intuitive. And also that basically good generalization, so the embedding Hilbert space can be small, but it can also be large, provided that somehow the embedding scrambles the information about X in a small dimensional subspace of the full Hilbert space. So this idea is kind of intuitive, and it was already conjectured, or I mean discussed in this paper by Lloyd and others, though without formal proof to the best of my knowledge. So in our analysis, on the other hand, this can be proven by some inequalities that link the fidelity to our quantities. So the conclusion is that, I mean, good embeddings somehow should cluster data from the same class into nearby points in the Hilbert space, like here and here and here, and separate different classes as much as possible. However, due to and this is an important point, due to the trade-offs between the approximation and generalization error, so this ideal picture here can basically never be achieved as long as the bias risk is different from zero, as we will see in these numerical experiments. Now, another result is the link with kernel theory. So for pure state embeddings, so we show that the generalization bound can also be expressed as the trace of a square root of this is what is normalized kernel matrix. And this, I mean, this result makes the calculation of B much easier for large dimensional embeddings. Then according to our theory, so the worst generalization is obtained when the kernel matrix is close to an identity matrix. But unfortunately, so K close to identity is quite likely when you have a large dimensional embedding. And so we should try to avoid this. So the take-home message here from this analysis is that so you should avoid as much as possible K close to identity because it's bad for generalization. And it also makes the problem a bit more trivial because it's almost linear. So you have to be extra careful because it's quite likely to get this condition for large embeddings. So another interesting conclusion is that in order to favor in order to favor generalization, so the final Hilbert space can be small, so must be small, but the initial one can be big. So what you can do is that you can iteratively discard information by quantum pooling layers, like the ones discussed here, so in this paper by Kong and others, which were at the basis of the quantum convolutional neural network, where somehow you optimize some disentangling unitary and then you get rid of some qubits in an iterative way. So using data processing inequality together with our entropic bounds, so one can show that the pooling does indeed favor generalization, but it harms the accuracy. And this again can be proven. So the take-home message here is that if you can obtain low training error by using these pooling layers, then use them, so use these layers, because generalization then can only be better. Okay, so finally, I show how our results are linked to what is called the information bottleneck principle, which is an information theoretic framework to study machine learning and deep learning in classical statistics. So the information bottleneck is based on the idea that the learning algorithm should squeeze as much information as possible about the input, so keeping only the relevant information to predict C. So quantum information bottleneck principles were previously discussed in these papers at the bottom, but for different reasons. What we have introduced in another paper, I think, is quite different. So for our problem, we can treat the quantum embedding, so the rho of X, as the bottleneck, okay? And the optimal embedding, according to the information bottleneck principle, is the one that minimizes the following Lagrangian, so this one here, for a particular value of beta. So you see that you should minimize the mutual information between X and Q and maximize the mutual information between C and Q. Now, how these two are, so how to put like a weight to these two is given by the beta. So beta somehow allows us to explore the trade-off between the approximation and the generalization. So we found that somehow the solution to this information bottleneck Lagrangian can be written as a kind of self-consistent equation, which is this one here, which is, I mean, not so easy to solve, but it can be solved by iteration for sufficiently small Hilbert spaces. So from our numerical experiment that you can see here on the picture on the right, so we see that the embeddings constructed by solving the above equation for low beta have large risk. So for instance, low beta here have very large risk, and small generalization error, small b, so small generalization error. While if you increase the beta, then normally the risk, so namely the approximation error, decreases, getting very close to the theoretical minimum error, which is the bias risk. But this comes at the price of a slight increase on the generalization error as measured by this bound B. So we can also see geometrically what happens in the block sphere. So here at the bottom, so you see that for moderate values of beta, so beta for instance 1.5, the embedding starts to cluster the data from close to each other, but without separating the classes, which here, I mean, the classes here are the red and the yellow points. But on the other hand, for large beta, the data are clustered and well separated, as you see in this example here with 2.8. But still, you see that there are some wrongly classified data. You see that there are some yellow points here, and there is also a red point here. And of course, you cannot avoid this because the bias risk is not zero. Okay, now, so we have seen some theoretical conclusions. Let's see also some more applications of our theory. So the first one is that of quantum phase recognition, where again the main task is to recognize the phases of matter in a quantum many-body system, but by taking measurements on the quantum many-body system itself. Now, we have considered a simple model, which is like a paradigmatic model from quantum statistical mechanics, which is the Ising model, the Ising model, the one-dimensional Ising model with transverse field. So here, L is the number of qubits, and H is the external parameter that one can tune. So this H is our X somehow. So this model is exactly solvable by fermionization, and it has two different phases. So the ordered phase where H is smaller than 1, and the disordered phase when H is greater than 1. And the critical point, H equal to 1, separates these two phases. So now, for this model, somehow, this is exactly solvable, so one can also go to very large L. So here, all the calculations are done for instance, like 100 qubits, where we also found that somehow the B, so the bound quantity, is roughly 6. So this model, I mean, is very simple to learn, okay? Because this B is very small. And indeed, I mean, one can get an intuitive understanding by studying the fidelity. So this here on the right, so this is the fidelity. So each point here is the fidelity between the ground states of this model for different values of X. Different values of H. So you see that basically the fidelity between two ground states from the same class is quite large, while the fidelity between two ground states belonging to different classes is quite small. So this, I mean, signals a good, an easy problem. So something that is easy to learn. And indeed, I mean, this number here is very small. So we have done a numerical check, and we used a fidelity-based classifier. Namely, we consider a number of training samples, so T training samples per class. And in order to classify a new data, So we calculate the fidelity between the new ground state and all the ground states in the training set. And then we take the class from the training set of the state with highest, so with largest fidelity with the new ground state. Okay. Now, in order to make the problem less trivial, given the simplicity of this picture, we also considered a finite shot approximation of the fidelity with S measurement shots. So you see from this picture on the right that even with a single training sample per class, and with, let's say, just 5 shots, so very noisy estimation of the fidelity, the testing error is basically negligible everywhere except close to the phase transition point and except to this 0 point. So if we increase the number of measurement shots, so if we make the measurement more precise, then basically these peaks disappear and it remains. You only have this peak here. Now remember that basically this was an upper bound on the number of training samples, and so we tried to put t equal to 5. And for t equal to 5, even with a very noisy estimate of the fidelity, you see that the testing error is almost 0 everywhere, except again to this close to this phase transition point when you have a small peak. So this somehow confirms the prediction of our theory that we can use this quantity in order to get an upper bound on the estimated number of training samples somehow. So this is basically then the final slide, the final technical slide of my talk. So we have also proposed a variational method based on the quantum information bottleneck principle that we have proposed. And so here, what we did was to use so we focused on classifying classical data. So we use this true moon data set, where somehow you have to decide whether, let's say, a point belongs to the green moon or to the yellow moon. And so we used basically what is called the data re-uploading quantum classifier, which is based on single qubits, and it was proposed in this paper here. So in the data re-uploading classifier, so you apply basically these gates to a state initially in 0. And all of these gates depend on the input x. And the way they depend, so here these gates are rotations around the z or the y-axis. And the way the input x is mapped into this rotation is via some linear transformation where the weights have to be trained. So we were able to train these weights by minimizing variationally the information bottleneck Lagrangian for different values of beta. And the result is shown here on the right. So for beta equal to 30, so large beta, so you see that basically this is again the fidelity. So the fidelity displays like a similar behavior to the one shown before. So you have a clear separation between the 2 classes. So states belonging to different classes have almost 0 overlap, while states belonging to the same class, they have a large overlap. And here you can see that also the testing error is pretty small, like 4.5%. But then also we did also something different. So we try, okay, so let's see what happens for small beta. So small beta, you see that the picture here is entirely different. So this, here we put the infidelity, and the infidelity here is pretty small. So it's something which is like 10 to the minus 7. So that's the maximum. It's something around here. So for this small value of beta, the model is almost constant, okay? And you remember that almost constant models, they are good for generalization. So you see that, so the take-home message here is that, so even this ideal picture is what somehow you see in papers. So somehow to favor generalization, so something different might provide better results. And indeed here, the testing error is smaller than the one, even though, from this picture, it seems that this should be larger. Now, this comes at the price that somehow estimating such low fidelities, however, is more difficult, and so we need more shots somehow. Okay, so let me jump to the conclusions. So we have introduced quantities from quantum information theory in order to study generalization and supervised quantum classification. And somehow the summary of our results are shown in this picture on the right, where somehow there is a trade-off between the approximation and the generalization error. And so then we have studied how the Hilbert space dimension, pooling layers, and also the amount of noise that I haven't discussed in the talk. So how all of these things affect the approximation and generalization capabilities of quantum classifiers built from data. So for instance, for larger Hilbert space, the approximation decreases, the generalization increases, and the opposite happens for using pooling layers and even noise. So of course, there are many open questions, like what happens in the deep learning regime. So one can study different cost functions, though I don't expect our results to be affected too much by the choice of the cost function, because basically the information bottleneck principle, which is kind of cost function independent, basically provides the same answer. And so yeah, so this is pretty much the results of my talk. So thank you very much for your attention, and yes, thank you a lot.
Thank you, Leonardo, for this very nice talk. And I have some questions. So my first question is that, is it possible to improve the generalization bound by reducing this I2, the learning information, to the usual mutual information? Because we know that the information bottleneck function is the balance between two mutual informations instead of like the learning information and the mutual information.
Yes. So indeed, I mean, we studied two different ways of somehow optimizing. So one is the formal way.
Yes.
So one is the formal way. So there is somehow an analytic solution to this equation, which is given by this self-consistent equation, which is nonetheless is quite difficult to solve. Okay. So I mean, I try to see whether there is I don't know, an algorithmic way of writing this expression, but I wasn't able to find a solution yet. So finding, let's say, something more efficient is also pretty much an open question for me. But from here, you see also the trade-off, and which is given by this beta. And you can decide how much importance you want to give to generalization by somehow putting either a large or a small beta. And the other way, which is simpler, is this variational method, where somehow you can train the information bottleneck Lagrangian for different values of beta. So I don't know if I answered your question. Probably I didn't get the question. So you were saying about
the theory
here,
part.
Yeah.
The theory part.
So here.
So it's there's a generalization bound for there's a I2 function, right? The learning information.
Oh, right. So yes. So what you're saying is that in the generalization bound, so here there is the I2, not the I.
Yeah.
Yes.
Yeah, exactly.
So I haven't tried to do the calculation with the I2. Actually, that's a good point. Simply because the I2. So why I haven't done that? I mean, numerically, I think one can certainly do that. The reason for that is that because, I mean, I believe that the fact that we have I2 depends on our initial choice of the loss, like the linear loss. I believe that for other choices of the loss, then one might get I. So I mean that was a bit. So I don't think there is much difference in training I2 rather than I. I think both should give the same kind of information. So the advantage of the I is that it has much more properties which are similar to the classical mutual information.
Yes.
While the I2 doesn't satisfy some properties. Does not satisfy all the properties of I. So because to do a check with something more with the classical theory, I said, okay, let's do the information bottleneck with the eye. But I'm sure that one can also do some with the eye too. I haven't done numerical experiments, so I don't know what can happen.
I see. Thanks. And okay, my second question is that if we don't know the embedding, then how can we do the learning? For example, we are given a bunch of states, and we know some of them are entangled state and some of them are not entangled. Then how well can we learn the separation between these two classes? Because we don't know
so
in general.
I lost the connection for at the beginning. So you said so for the entangled states, you said, right?
Yeah.
So for the entangled state, yes. So for the
Mm.
entangled state, I haven't done numerical experiments, so I cannot use that more like a driving principle. But I mean, this is pretty much something that I think is interesting to check, like how also the problem is so how this classifier works with entangled state. But I haven't done numerical check. So just to say that how all these quantities here, they basically depend on these probabilities. So if you know the probabilities, then it's fine. But here, for instance, in the numerical part, where we don't know these probabilities, so here, basically, what I did in order to, let's say, minimize the information bottleneck Lagrangian is, of course, to approximate that with the data-driven version. So instead of having averages here, let's say, with respect to the P, you substitute that with averages over the data. And that's exactly also what I did here for estimating this B function. And so I tried to increase the number of data points, and I see that basically this value of B at a certain point converges. So it seems that somehow these predictions are stable with respect to, I mean, trying to do the calculations from the data itself for estimating these quantities, even without knowing the P, which is the entire point of the idea.
Okay.
Yes.
Thank you. And I'm very interested in the asymptotic regime that in your last slide. But so okay, so let's assume that the embedding maps each x to row x tensor n. So we have many copies. Then I can expect.
Let me go.
To this slide.
Yeah.
Yes, something like this. So I can expect that the approximation error will go to 0 as n increases, right? But then we know that the mutual information or even the raining information is additive for these tensor product states. So from the generalization bound, we can see that the generalization error will increase.
Yes, indeed. I mean, this is something that for me is currently a pretty much open question. So my current view on this is that somehow doing something like this might be even, I don't know, kind of an overfitting. So we are using something which is too complex. So we should somehow use a simplified version of this pi. I don't know, maybe some right. So we have somehow to also improve the theory for doing the asymptotic, because so one can basically, I mean, take a suboptimal value of the pi where you perform a local measurements, and then you do some post processing.
I see.
And then this is definitely connected with the classical part. While on the other hand, if you perform, let's say, full measurements, first of all, the problem might have don't have any solution, or might be too complex, and then, as you said, using additivities of so forth, we will always end up. We might always end up in this regime here. So, I mean, this asymptotic analysis is pretty much an open question for me, and it's something very interesting. And I guess that one should also get some intuition from, indeed, from information theory, in order also to check how to, I mean, fully exploit in a better way the fact that we are always using copies in a quantum machine, because I mean, even if you're using measurement shots, these are copies, right? And so, but this is pretty much the question for me.
Yeah, we don't know if many copies help in a learning scenario. That's the main point.
That's another important, very important aspect. And yes.
Okay, is there any questions from the audience? Okay.
I may have. Sorry,
Sorry, I cannot hear. There is like a background noise.
Okay,
sorry, I have a very naive question about the generalization part. Is it some kind of information describing the state, or is for the system? Because you mentioned the system, Hamiltonian system later, there is also a bound, so I'm confused. Is it describing some information for the bound? What's the meaning of it? Can you elaborate more?
Right. So there are two ways of seeing this this problem. So one way is that you fix the embedding. So you fix the mapping between x to rho of x. Okay. So this is fixed. This is fixed. For instance, it's given by the nature. So for instance, in the self-driving car example, I mean, that's the input state that you get from the outside world. So somehow it cannot be improved. It's something fixed and given by nature. So in that case, what you optimize is over the measurements. So you optimize over the pi c, okay? And so for a fixed embedding, then so you can always split the average testing error, which is the average loss for the optimal classifier. So the optimal classifier here would be a P of n, and depends on the training inputs. So and this error, it's basically the entire part here. So this entire error is the sum of the bias risk, the approximation error, and generalization error, which have different meanings. Okay, so now so this is for a fixed embedding, and I mean, here you say, okay, so I have this, and I cannot really improve anything here, so I cannot act on the generalization. So I simply have to get more data in order to make this quantity small, so I have just to increase t. But then in the information bottleneck principle, on the other hand, this mapping is not fixed, but you can also optimize this by assuming that you use something like the optimal discrimination strategy. You optimize the way your classical input is put into a state. And this is somehow good for instance, for what is that? For this application part, where somehow the way your input data is put into the classifier somehow can be trained. So in that case, so the information bottleneck principle, for instance, helps you not just to find the optimal measurement, but to find somehow the optimal embedding. So I don't know if I answered your question or if it was...
Yeah, okay. Yeah, I think it's clear. Thank you.
Okay, thank you.
Any questions from the audience? Okay, if not, then let's thank Leonardo for this very fantastic talk.
Thank you.
I hope we can I can see you someday.
Yes, now I can also see you. Okay, so I can.
Yeah, and we are hosting the QIP 2023